Hello everyone, welcome to video lecture number 4 of Strength of Materials. In order to design any component, we need to know the properties of the material what we are using. So how do we know the materials, or when we have a material, how do we test it to know its properties? So one of the very basic test is called tensile test, which will be conducted on a machine called UTM, Universal Testing Machine. Many tests can be conducted on the same machine. That is why the name universal. Tension test, compression test, shear, bending, all types of tests can be conducted on that machine. Tensile test, when I say, there is a standard procedure to conduct test on any specimen. So you need to use a specimen of this kind for tension test, and it is subjected to loads like this, tension load P, by fixing it on a UTM. This portion is used for fixing. Specimen need to be held inside a shackle or chuck in order to apply the loads. This is the region where we use it for measurement. When as we apply the load, we will measure the deformation in this region. And for measurement, we have to use two specific points. We normally mark a line here, mark another line here. So this length where the deformation is measured on the specimen is called gauge length, initial gauge length L0. And diameter of this specimen, this is called initial diameter of the specimen. After these measurements, the specimen will be loaded onto the machine and load is increased gradually. Readings load P in Newton and deformation DL in mm are noted down. Initially there will not be any load, so DL will be 0. Gradually load P is increased from 0. It is called quasi-static loading. You should not load the specimen suddenly. So gradually it is increased. Let us say a load of 10 Newton is applied. Deformation observed. I'll just write some random value. Next, load is increased to 50 Newton, 0.00015, let us say, and load is increased to 500 Newton, let us say 0.001, load is increased to 1000 Newton, 0.002, and so on. So like this, it is slowly loaded till the specimen breaks into two pieces. Till that point, it will be loaded. And this deformation is measured using some instrument, normally dial gauge. Now you just understand that dial gauges are used for measurement, and we have measured the deformation. After having load and deformation and original dimensions of the specimen, we can always calculate what is the stress. Stress sigma is equal to P by A, Newton per meter. This can be calculated. So A is by D0 square by 4 because it is circular in cross section. And strain also can be calculated. Strain is epsilon is equal to DL by L0. DL is here. We have measured it. The L0 and D0 should be measured before the test. Now we have to use them for calculation so we can get the values of strain also. So all the stresses and strains are calculated now at this stage, and it can be plotted on a graph. That is called stress strain diagram. The uniaxial tension test is conducted to obtain information regarding the mechanical behavior of material. Standard specimen is subjected to gradually increasing load, and the values of loads corresponding to the deformations at regular intervals are noted. A plot of stress versus strain is drawn. So we'll see how it looks like. For typical mild steel specimen, I'll draw the x and y axis here. Yeah, this is the x axis and this is the y axis. I have to write strain here. X axis is strain and y-axis is stress, sigma. Initially, when the material is elastic, we know that specimen undergoes deformation which is elastic, means it can recover, it can come back to original size and shape. And also, we know the Hooke's law, which says that stress is proportional to strain within the elastic limit. So based on that, when we plot the stress strain diagram, initial portion will be a straight line like this. I call this point as O. And there will be a point here very close to this point, can be called as proportional limit A, and B is called elastic limit. So beyond B, no more the material will be elastic. That is why it is called limit of elasticity or elastic limit. And after that, if you continue to plot, it goes like this. It will come down slightly and then again it goes up and it takes a peak value. And if you continue to load, it comes down slightly and at some point here it breaks. This is the breaking point, and this point here is called upper yield point C, and a point here called lower yield point D, and this ultimate point, maximum stress, is point called ultimate stress point. The last point where the specimen breaks is called fracture point. which is denoted by the letter F. This portion, line represented by endpoints OA, that is the elastic or the region where stress is proportional to strain. Hooke's law is valid. And beyond that, to a small distance, you will find another point where the material is elastic, that is point B. If you continue to load the specimen, it will follow the path BC. At C, it continues to deform, but the load will not be taken, strain will be more. That point is called upper yield point C. At point D, which is called as lower yield point, that is a point where if you continue to load, load also increases, deformation also increases gradually. That is the path DE. At point E, the stress experienced in the member is maximum. That is why it is called ultimate stress point. And if you continue to load, after certain strain, the specimen will be separated. So how does it look like when it separates? Specimen will look like this. There is something called cup and cone fracture and brittle fracture. Here you will see cup and cone fracture. One portion will be like this and other portion will be like this. So that is how the materials separate. That is the failure point. The point O is the origin where we start loading. Point A is called proportional limit. It is the maximum stress level up to which the stress is directly proportional to strain or Hooke's law is valid. Point B is called elastic limit. It is the stress level up to which deformations caused by the load disappear, or it is the greatest stress up to which the material exhibits the characteristic of regaining its original shape and dimensions. Normally in experiments, you will not be able to separate them clearly. They will be almost same, point A and B. Point C is called upper yield point. The value at which the material continues to deform at constant load. At the point C, strain is observed, but if you look at the Y component there, it is almost same or it is even decreased. That is why it is called upper yield point. It is a value of stress at which the material continues to deform at constant load. So this stress, whatever is observed here at point C, that is called yield stress. Sigma Y is a material property. For example, steel will have a yield stress of around 250 or 350 megapascal depending on the composition. And point D is called lower yield point. So observe at point D, if you continue to load, it takes the load. At point C, load will come down, but deformation is observed. But at point D, if you load, it takes the load, the strain also increases along with that. That is why it is called lower yield point. Point E is called ultimate stress point. It is the maximum stress induced in the specimen and it occurs in the plastic region before the elastic region, that is B here. This region is called elastic region, and beyond this till the fracture point, this is called plastic region. So E is called ultimate stress point and F is called fracture point. This region from C to D is called yield region. Between D and E, this region is called strain hardening region. Between F and E, this region is called necking region. Specimen in this region, E and F, will be like this. Before fracture, this kind of neck is formed. This is called necking. Then it separates. That phenomenon is observed in the region E and F. That is why that region is called necking region. See, in order to use any new material, you have to do a tensile test, you have to do a compression test, you have to do hardness test and so on. There are so many tests you have to do, then only you can use it for your application. The typical stress strain curve observed for mild steel. Mild steel is a soft material. It is supposed to be a ductile material. Ductile material is a material which undergoes considerable amount of plastic deformation, or it is a measure of material's ability to deform. So mild steel is a ductile specimen, so it undergoes considerable amount of plastic deformation. That is why beyond this point C, point D, point E, point F, all those points can be clearly seen in the stress strain diagram. But if you take other specimens, you may not be able to see the yield regions separately, or sometimes immediately after ultimate stress itself, the material may fracture. So this E and F band will be very, very small and so on. So in order to show these points separately, I have considered specific material, that is mild steel. We will see how this stress strain diagram is observed for other materials. This is strain axis and Y axis is stress. So for other materials also, initial portion will be straight line only. For example, I'll write for aluminium. will be like this. After that, it will not show a clear-cut yield point, but it continues like this. And at some point, it breaks here. This is the kind of stress strain diagram you see for aluminium. And for cast iron, if I write, cast iron is another material with high carbon percentage. So you will see a slightly different path of stress and it fails somewhere here. So this is for cast iron. And for high carbon steel, more carbon percentage is present in some steels which are called high carbon steel, for which you will see the stress strain diagram somewhat like this. This is for high carbon steel. Here in the previous diagram for mild steel, slope if I measure here, we will get Young's modulus or modulus of elasticity. So for steel, we can measure it from this diagram. For aluminium, we can measure it here. Cast iron Young's modulus here. We can measure the high carbon steel Young's modulus here. So I'll just write it as EHCS, high carbon steel. This is E cast iron CI. This is E aluminium. Along with Young's modulus, you have two more parameters. One is called tangent modulus and second one is called secant modulus. See, for any material, after drawing the stress strain diagram, at any point on this stress strain diagram, I'll show it in a different color, pink color. I am marking this point P. If I draw the tangent, we know how to draw the tangent to a curve. This is a curve. I'm drawing a tangent there, and that tangent will have certain slope. Angle of this tangent is called tangent modulus. So slope of the tangent drawn at any point of interest on the stress strain curve is known as tangent modulus. So tangent modulus will be different at different points. Let us say stress strain diagram is somewhat like this. I'll take the point of interest here. I'm marking it in pink color. If I draw a line joining that point of interest to the origin, like this, slope of that line, if I measure, which is called secant modulus. The slope of the line joining the origin and the point of interest on the stress strain curve is known as secant modulus. Now we will try to understand what is a ductile material, what is a brittle material. In ductile materials, considerable amount of plastic deformation is observed. That is why you are able to draw them into sheets or wires. Because of plastic deformation, it will not suddenly break. Next example is a chocolate. A chocolate, when initially, if it is like this, if I subject it to bending load like this and release the bending load, it will take a deformed position like this. It will not break. But when we give example for ductile material in strength of material, it is better to give engineering materials. So best example is mild steel. We have seen that. Low carbon steel. Next, brittle material. So any material which do not show considerable amount of plastic deformation can be called as brittle material. They suddenly break without much plastic deformation. Very less amount of plastic deformation before fracture. Example for brittle material can be graphite or non-engineering material. If you want, I can give an example of a biscuit. If you take the example of biscuit, if you apply the bending load, it suddenly breaks. It will not deform like a chocolate. So that is a brittle material. But engineering material, as more familiar material for mechanical engineers, is high carbon steel, HCS, cast iron and glass. See, after conducting a tension test, we measure two parameters. One is called percentage increase in length. We measure this after the fracture point. We keep the specimen and we join and we measure the length. What is the final length? Based on the final length, we'll find out this percentage increase in length. The formula used for this calculation is final gauge length minus initial gauge length divided by the initial gauge length expressed in terms of percentage. So into 100 will be there. So it is basically final gauge length minus initial gauge length divided by initial gauge length into 100. This is called percentage increase in length. Ductile materials will have more percentage increase in length. So that is why this is one parameter which can be used for identifying how much brittleness a material has or how much ductile nature a material has. One more parameter is there similar to this, which is called percentage decrease in area. See, when a specimen is undergoing deformation, stretching, its lateral dimension decreases, diameter decreases. After fracture, we can identify how much a decrease in area has happened. That is another measure of brittleness or ductileness. So the equation used for calculating this percentage decrease in area is initial area, because initial area will be more than the final area. So final area divided by initial area into 100. Or in the mathematical form, I can write it as A naught initial area minus AF divided by A naught into 100. This is another parameter. It's called percentage decrease in area. Now just observe, I'll write a bar here, and this area of cross section is A, and it is subjected to a load at the center like this of magnitude P. Here also there is a face, and from that face I have the equal and opposite force P. And let us say the length of this specimen, then length of this bar is L, and the material property, Young's modulus of this material is E. I want to find out an expression for the deformation in this bar. By definition, stress sigma is equal to P by A. P is the applied load, normal load, and A is the normal area of cross section. Stress is defined like this. Now, what is strain? The definition of strain is epsilon is equal to dl by L, change in length by original length. So this is longitudinal strain. Also, we have Hooke's law. Sigma is equal to E into epsilon. E is the Young's modulus. Now, I need to combine all these three equations and get an expression for the change in length, that is dl. If I write E into epsilon is what? dl by L, and sigma is what? P by A. Now if I separate dl from this, dl is equal to P into L divided by A into E. This is the expression for deformation in a bar of constant cross section subjected to load P. So with this background, we will try to solve a problem now. A tension test was conducted on a mild steel specimen. The following data were obtained from the test. Diameter of the specimen 16 mm, load at proportionality limit 72 kilonewton, load at failure 80 kilonewton, diameter of the rod at failure 12 mm, gauge length of the bar 80 mm, extension at a load of 60 mm is 0.115 mm. Final gauge length of the bar is 104 mm. Determine Young's modulus, proportionality limit, true breaking stress, and percentage elongation. The diameter of the specimen means this diameter is 16 mm. Load at proportionality limit means if I try to locate that in the stress strain diagram for tension test, load at proportionality limit means here this load is given. At this point, P is given as 72 kilonewton. Load at failure is at this point 80 kilonewton. And diameter of the rod at failure means after deformation, the specimen would have deformed like this. And diameter of the rod will be reduced because it is tension test. After failure, you join the specimens and measure, this becomes 12 mm. See, originally it was 16 mm. It has been reduced to 12 mm after deformation. Gauge length of the bar is 80 mm. This is measured as 80 mm. And extension at a load of 60 kilonewton is 0.115. And this 0.115 is nothing but DL. And this DL value is given at a load of 60 kilonewton. You see here in the stress strain diagram, this proportionality limit is corresponding to 72 kilonewton. And this value is 60 kilonewton. 60 kilonewton is less than that. So it will be somewhere here. So here, load is given as 60 kilonewton. And at that point, what is DL? DL is given as 0.115 mm. Final gauge length of the bar means if I measure in this specimen after failure, if I measure this distance will be 104 mm. Originally it was 80 mm. So this is LF, this is L0, and this is D0, and this is DF. First, if I want to calculate what is Young's modulus. Young's modulus is what? It is a slope in this region, or stress by strain. You have to calculate stress and strain, divide stress by strain, you will get Young's modulus. But that should happen within the elastic limit. Load of 72 kilonewton is the elastic limit. At 60 kilonewton, deformation is 0.115 mm. So I can use that data and find out stress and strain, and through that I can find out what is the Young's modulus. So within elastic limit, I can calculate what is the stress. Stress becomes P by A0. It is 60 into 10 power 3 divided by A0 is what? Pi into D0 square by 4. So pi D0 is how much? 16. So 16 square by 4. To calculate this will be in terms of Newton per mm square. Strain also you can calculate. What is strain? Strain is dl by L. 0.115 mm. What is the original length? This is L0 actually. So L0 is 80. So you calculate what is this. Strain has no unit. E is equal to sigma by epsilon. So substitute and find out what is the E. We are supposed to get a value of 207.593 into 10 power 3 Newton per mm square, which is equal to 207.593 gigapascal. Next, we have to find out proportionality limit. Means at this point, what is the stress that I have to find out here? For which I need the load at proportionality limit and the original cross-section area. That's all. I'll call it as sigma P. P stands for proportionality limit, which is defined as load at proportionality limit divided by original area A0. 72 into 10 power 3 divided by original area. Area is what? Pi into 16 square by 4 comes out to be 358.1 Newton per mm square. Then true breaking stress, it means that it is a ratio of breaking load to the area of cross section at that instant. True breaking stress is equal to breaking load divided by true area at that instant. Numerator becomes 80 into 10 power 3. Denominator becomes pi into 12 square by 4, not 16 square by 4. Now it is reduced. Comes out to be 707.35 Newton per mm square. Last one is percentage elongation. The equation is final length minus initial gauge length divided by initial gauge length into 100. So it is 104 minus 80 divided by 80 into 100. If you calculate, you will get around 30%. Okay, this is the second problem. Tensile test data is as follows. Diameter of the test specimen 25 mm, gauge length 200 mm, extension at a load of 20 kilonewton is 0.004 mm, maximum load 225 kilonewton, neck diameter of the specimen 18.25 mm, load at yield point 150 kilonewton, length of the specimen after failure is 275 mm. This is a tension specimen before loading. And this is the tension specimen after loading. After failure, if you join the separated parts, it looks like this. Its length is increased, cross section is reduced. This is called L0. And original diameter of the specimen is called D0, which is 25 here. Gauge length is 200, means L0 is 200. Extension at a load of 20 kilonewton is 0.04, means somewhere here. Load is given. P is equal to 20 kilonewton and DL is equal to 0.04 mm. That's given. Maximum load is 225, means here to calculate ultimate stress 225 kilonewton, and neck diameter after failure, if you join the specimen, your specimen will have a neck like this, and this diameter is 18.25 final diameter, and load at yield point at this point 150 kilonewton, and length of the specimen after failure means this length is now 275. Originally it was 200. Yield stress is what? It is the load at yield point divided by A0. 150 into 10 power 3 divided by pi into D0 square by 4, 305.58 megapascal. Second, ultimate stress can be called as sigma U. So what is the definition of ultimate stress? It is a load at ultimate point divided by A0. 225 into 10 power 3 divided by pi into 25 square by 4, 458.36 megapascal. Percentage elongation is final length minus original length divided by original length into 100. So 275 minus 200 divided by original length is 200 into 100, 37.5%. Next is percentage reduction in area. It is defined as original area minus final area divided by original area into 100. And original area is pi by 4 d0 square, and final area is pi by 4 df square. I will take pi by 4 outside. 25 square is 18.25 square divided by original area, which is pi by 4 into 25 square into 100, 46.7%. You can also calculate Young's modulus in this, because Young's modulus E is equal to stress by strain, right? And what is the stress there? It is load by area, and load is 20 kilonewton. So 20 into 10 power 3 is load divided by A0. A0 is y into 25 square by 4 divided by dl by L 0.04 mm divided by 200 mm. You will get a Young's modulus of 203.72 into 10 power 3 Newton per mm square.